We are today going into the first controller, which is PI controller. This is actually an introduction to PI controller. Last week, we have looked into the gain adjustment control. In gain adjustment control, we use root locus. Imagine this is the root locus, the one on the first figure, root locus. We can design A. Let's say we want overshoot. We give percent overshoot. Then we can draw a zeta line and then get point A. Then by using point A, we can get the dominant pole. And also we can get the value of K. That is by using gain adjustment. And we can see that when we adjust K, the root locus or the closed loop pole, it changed according to the root locus. It must be on the root locus, which is in this case on the blue line, root locus. So that is one disadvantage of gain adjustment. It can only be on this root locus. It cannot be outside the root locus. Because when we adjust K, when we change K, it will be on the root locus. Therefore, with the gain adjustment, we can only obtain, for example, settling time at A. We can only find at A here, okay, for a certain overshoot. Let's say this is the overshoot, then this is A. If I want another overshoot, let's say here, then I will get another point here, and then I can calculate settling time and also peak time. But it must be on the root locus. Now imagine that I want my closed loop pole at B. Okay? Imagine that I want at B. I don't want A. You can see if I plot the response, B is better than A. Although they have same overshoot. Why same overshoot? Because they are on the same zeta line, same zeta, that means same overshoot. But settling time, you can see here, settling time here is better because zeta omega n is bigger. Okay, settling time, Ts, 4 over zeta omega n. So when zeta omega n bigger, when the pole is far from the origin, then the settling time is smaller. System is faster. Also, we can see here, this is J omega D, in which peak time pi over omega D. Omega D is bigger than A. If the omega D is bigger, then TP is smaller. Smaller means fast, peak time. So when we plot, we can see here B. You can see the at B, settling time is better, is faster, peak time better. So B is better, point B is better than A, but it cannot be obtained by using gain adjustment. There is no way I can find point A as my closed loop pole if I use gain adjustment. Because gain adjustment, it will be only on the root locus. Therefore, in order to get B, I need a controller. We call controller, or sometimes we call compensator. We have to design a controller or a compensator in order to change to get the desired point, desired closed loop pole, which is not on the original root locus. This is the introduction to why we need a controller. Okay. Now, how can we improve the time response? Let's say I want from a closed loop pole at A, I want to change at B. How to do it? It can be done in two ways. First, we call by cascading compensation, by cascade. Cascade means we add controller here in series with the plant. This is the system. And we add in series. We put compensator or controller in series with the system. So that is one technique. And normally this is just K. When this is K, we call gain adjustment. But now we know the limitation of the gain adjustment. We want to design another controller, not just K. Okay. That is the first technique. The second technique is by using feedback compensation. Feedback means we add at the bottom when in the feedback line. We add controller, compensator or controller. Okay. Both techniques can be used. We can see that later when we apply either one, we can change the open loop pole and zero. Now when we change the zero, the pole will be different. Root locus will be different. And we can design a controller so that the root locus will go through the desired closed loop location, desired closed loop poles. I mentioned we can use two techniques, but in the subject we will use this one. In 3143, we will use the one which is in cascade. Although the other one can also be used, we will just focus on one which is in cascade. That means our controller will be in series with the plant or with the system. Okay, before we move into PI controller, I want to take some time to revisit steady state error. This was discussed in the previous control subject, 3133. Hope you still remember steady state error. Remember, if this is the system response, this is input. This is the output. The error is the difference between input and output. If this is input RT, output CT, error is RT minus CT. Input minus output. When T approach infinity, that means after a long time, we take input minus output. That is the steady state error. And our aim is steady state error equal to 0. That means we want, if this is, that means what we want is, if this is the input, the output is the same. Finally, go to the same point. That means input equal to output. This is a case where where error equal to 0. That is our ultimate aim. We want error 0. That means, for example, if a robot, I want a robot to move to 2 meters. If the robot is good, it can move to the desired position 2 meters. That means error 0. If we want 2 meters, but it go to 3 meters, then 1 meter error. That is not good. And there is a formula to calculate steady state error. Steady state error is calculated based on this formula. Hope you still remember, where ES equal to RS input minus CS output. And this formula is known as the finite value theorem. I believe your lecturer, I think Dr. Herman, last semester have taught you steady state error. And the steady state error is depend on the input. It's very much related to the input. Okay? And we have three different input. The first one, step input. Okay, the one I drew here is the step input, in which error equal to, sorry, I missed something. Depend on input for a unity feedback system. Now we focus on unity feedback system. Okay. They are also related to input. Step input will be limit I will wait. Yeah, start from here. For a unity feedback system, error can be summarized into limit S to 0, S multiplied with RS, 1 plus GS. Okay, please look into your notes, your previous note. And we have three input, step input. If step, then the error is equal to, because step S or RS equal to 1 over S, then we get limit S to 0. We cancel S here, become 1 over 1 plus GS. And it will be, I can put it here, 1 the limit GS. The same, I just put limit at the bottom that associate with GS, because the other one is 1. This is equal to 1 plus 1 plus KP. I'm not sure whether Dr. Herman has introduced you to KP, but in steady state error, this part, limit S to 0 GS can be equate to KP, in which KP is limit S to 0 GS. And KP is known as static error constant, Kp. Okay? P refer to position. Position refer to step input. So you will need to know Kp because the error will be given in terms of Kp. Once you know Kp, you can calculate error by using that formula. If we proceed to, we have the second input, which is ramp input. Ramp input Rs is 1 over S squared. The error, it will follow the same procedure. The error will be 1 plus limit S to 0 SGS. Okay, I have substitute into this formula, you get this. And can be written as 1 over KV, where KV is limit S to 0 SGS. This is another static error constant. V refer to velocity. Why velocity? Because we are using ramp input. We actually differentiate step. We get ramp position, then we differentiate, we get ramp. Okay, we call KV. Next is the third input, which is parabolic. I actually revisit. I think you should have known this, in which Rs equal to 1 over S cubed. And the error, if you use the same procedure, apply, substitute into that formula, you get 1 over limit S to 0 S squared GS. And this can be summarized into 1 over Ka, where Ka is 1 over limit S to 0 S squared GS. Ka. Ka also is a static error constant. A denote acceleration. So we have position, we have velocity, and then we have acceleration. Position, velocity, acceleration. Ka, Kp, Kv, Ka. So please revise this. Maybe Kp, Ka, maybe the static error constant are new to you, but they are just to summarize that formula. Okay, just Kp equal to limit S to 0 GS, so that I can write 1 over 1 plus Kp. All this is summarized in here in this table. Okay, we can see step input 1 over 1 plus Kp, ramp 1 over Kv, parabola 1 over Ka. Okay, the one that we just derived. Okay, now let's look into what is system type. Okay, anyone? Based on the transfer function GS, what is the system type of this GS? Anyone can help? System type. I believe you have done this in 3133. Anyone? What is the system order? For this transfer function, what is the system order of this transfer function? Thank you, Najeha. Third order. The highest order and the highest order of the denominator, that is the system order. Next, what is the system type of the transfer function?
One.
One. Why one? Which one?
If factorize the post equation, then you will get only 1s.
Okay, we take the denominator again, then we try to represent in this form, okay, as 2s plus 5. Here is power of 1. Thank you, Connie. This is known as system type. For this one, type 1. Okay, the second one, type what? What is the system type? For this, for another GS, another transfer function. Type 1, 2, 3.
0.
It is type 0 because it is actually s to power of 0. Okay. So please revise that. I'm not sure whether you know or not. You did not respond, only one responded. But you have to know system type. Yeah, I'm sure Dr. Herman has taught you system type. This is a common general knowledge. Okay, why we want to look into system type? Because beside the input, the system type also, the error also depend on the system type. Okay, let's see. I will erase all this. The error is 1 over 1 plus Kp. This is for a step input in which Kp is equal to limit s to 0 Gs. Okay, let's see Gs. Let's take Gs system type 0. Type 0. Let's take type 0. Example, Gs equal to 2 over s plus 2 plus 3. This is example of system type 0. So if I calculate Kp here, I have to apply limit s to 0, 2 over s plus 2, s plus 3. Then substitute 0, I get 2 over 6. Kp is 2 over 6. Then error will be 1 over 1 plus 2 over 6 is 0.33. 1 over 1 plus 0.33. So 1 over 1.33. This is the error. Okay, when when the system is type 0. Let's take another example when the system is type 1. Just take any examples. Type 1 means 2, s plus 2, s plus 3. That means we have s to power of 1 here. Okay, type 1. I will calculate Kp again. Kp limit s to 0, 2, s plus 2, s plus 3. Now when we substitute 0, because there is k at the denominator, because there is an s at the denominator, we substitute 0, it becomes 2 over 0, become infinity. When Kp infinity, error will be 1 over 1 plus infinity will be 0. Okay, 1 over infinity, we assume 0. Similarly, if type 2, of course, s to power of 2 here, then the same. We substitute 0, become infinity, then error becomes 0. This is shown here. Okay, 1 over 1 plus Kp. When system type 0, we get Kp some value. Here, for example, 0.33 here. Then we get error. There is a value also. When system type 1, here, Kp infinity as the one that we shown here. Why infinity? Because there is an s. And subsequently, error will be 0. Similarly, for type 2, Kp infinity, error 0. Okay, remember that our aim is to have 0 error. Okay. So, if I use step input, I can get 0 error if my type become 1 or more. If my system is type 0, I will not get 0 error. I will get a value. Okay, the value will depend on Kp, on the port and 0 also. But I will not get 0 error. I can only get 0 error if my system is type 1 and above, type 2, type 3, and so on. Similarly, if you use the same procedure for RAM input, because RAM now KV is limit S to 0, SGS. Okay, there is an S here. For KP, no S. SGS, that means this S need to be cancelled. If you type 0, you will see KV 0. Okay, and error infinity, no use. We will not use that type. But if you use type 1, KV, there is a value, and the error 1 over KV, and it will be 0 error if we have type 2, because KV will become infinity if type 2 system. You can try similar to the one that I did here for the step input. Error will be 0. That means for RAM, in order to get error 0, the system have to be type 2 and above. For parabolic or parabola input, type 1, type 0, type 2, type 0, 1 will not give 0 error. Type 2 will have an error, still not 0. Type 3, if you proceed with that, type 3 will give 0 error for parabola. Okay? So here I want to show to you, to describe to you that error can be improved, 0 error can be obtained by increasing the system type. First step, by increasing system type 0 to 1. RAM from 1 to 2. Parabolic from 2 to 3. Then we get 0 error. That is the basic theory, the basic concept in designing PI controller. Okay? We want to increase the system type. Then let's move into the first controller, PI controller. Why we did just discuss steady state error? Because PI controller, or sometimes we call compensator, is used to improve steady state error. That is the aim of PI controller. When people say PI controller, that means they want to use that controller to get 0 error, to improve the error. Okay? How to improve the error? As we have just discussed, error can be improved by increasing the system type by 1. Okay, let's say step input. I need to increase from type 0 to type 1. Increasing the system type. That is the only way we can get 0 error. How to increase the system type? Let's say I have initially system like this. Just now we have 2s plus 2, s plus 3. 2, s plus 2, s plus 3. Okay, this is our original system. Error, of course, not 0. When I use step input, error not 0. How can I get 0 error? I can get 0 error by increasing the system type. That means I want my GS now become 2 over S, S plus 2, S plus 3. I want to add S here so that I can increase the system type. How can I do that? I can increase S by adding a controller here before the plant, 2s s plus 2s plus 3. I can add by give value here, k any value over s. See, I add over s. If I can add over s here, then the denominator will become this. And if I give input step, output will give 0 error. That is the concept of PI controller. That means what this means, if we want to draw to plot pole and 0, -2, -3, this is the original system. When I add S here, that means I add another pole. Pole on the origin. Okay, so this is what I meant here. How to include the system type? By placing one open loop pole at the origin. So PI will add a pole at the origin. So the basic concept is S, 1 over S. And in control, there is one what we call one familiar term, 1 over S. A block of 1 over S is called integrator. In MATLAB letter, you find 1 over S. That block is called integrator. Okay, actually, you integrate. Okay, that means letter from type 0 become type 1. However, we can see later in another slide, in the next slide, by adding pole at the origin, that will affect the transient response. Overshoot, settling time, peak time will be affected if we add pole at the origin. So this is shown here. Consider this is an original system. GS, and the bottom one is the root locus. Let's say A is our point. Here, our interested point, our interested closed loop pole. We can get TP here, pi over omega D. We can get, if we know zeta omega n, we can get TS, 4 over zeta omega n. If we know the line here, we can get zeta, then we can get overshoot. Okay? So this is the original system. As we want 0 error, 0 steady state error, then we add a compensator or a controller. Okay, see, they put K over S. K is to be determined later, any value, but the important one is the S. Okay, S equal to 0, that means a pole at the origin. So here we add another pole here at the origin because we add S. And if we add pole here, we can see that the root locus now will be different because we have 4 poles. And the first 2 will meet each other, will have breakaway point. Another 2 also will have another breakaway point. if you calculate, you have asymptote. There are 4 asymptotes, and the angle is 45 degrees. 45, 135, 2, 225. So we have 4 asymptotes. And A here is not on the root locus anymore. Okay? It's now here. The one that sorry, no. A is not on the root locus. It is now different. Different pole. If this is the zeta line, here is the closed loop pole with different new P, new TP, new TS. That means by adding pole at the origin, by adding a pole at the origin, the transient response changes, berubah, can change. Not the same as the original one. But our aim in PI controller is to have 0 error, and we want to maintain the transient response. But here the good thing of this is 0 error. Error is 0. But TP and TS can change, which we do not want that to be happen. So how can we solve that problem? It can be solved by adding a 0 close to the pole at the origin. That means now I add, let's say 2. We add 1 pole here to get 0 error. Then we have to add another 0 near to the pole. Very small value. Why we add that? Because we can make sure, sorry, just now there are 3. Because we want to make sure the root locus here is only from pole to 0 here. Then it stops. Okay, then we have here root locus here, and again it will be something like this. It will be the one drawn here, and it can be, if you see, it can be similar to the one here, to the original system. Okay, although we can admit that it will be slightly different because of adding pole and 0. So here we can see this is pole and this is 0. 0 here is a small value. Then we can maintain the root locus, and we can get the same A point. Then we get same TP, same TS. And the good thing also, we get 0 error, because now we have increased the system type from 0 to 1. So this is called PI controller. That means, in short, GS is S plus A over S. Is PI controller. A is the one we have to determine A. But there is no calculation to find A. A is small value. A is a small value. Usually A equal to 0.1 or 0.5 or sorry, 0.5 is too big. 0.1, 0 or 0.01 in between, or 0.05. Small value. There is no way to calculate. We can just use that value. Okay? In the exam letter, normally the value is given, or if not given, then you can use any value, any small value. The smaller is better, okay? Near to zero. The aim, as I mentioned, is to make the root locus stop from pole to zero. The one affected from the effect of adding pole at the origin. So that is PI controller, the concept of PI controller. Now we do one example. Let's see what happened on the use of PI controller. We will take a break, 10-minute break, before we continue with this example. Any question before we take a break, before break?
No, doctor.
If not, we take a 10-minute break. Let's do this example to improve your understanding. Given a system with damping ratio 0.174, show that the addition of PI compensator or PI controller reduce error to zero for a unit step input. We normally give input without affecting transient response. So PI controller is used to achieve zero error and without affecting transient response. This is the one before compensator or before controller, and this is the one with PI controller. You can see that here is S plus 0.1 over S. A here is chosen as 0.1. Okay, 0.1 small a, small value. As I mentioned, there is no formula to calculate a, is just a small value. In this case, it was chosen as 0.1. So now this is the one before controller. This is the one after controller, after we apply a controller. In this subject, design of PI controller, later PD controller, and also PI controller, PID controller will be based on the root locus that we have just learned in the first topic. This is the root locus without a PI controller. We have, you see, our pole is -1, -2, -10, -1, -2, and -10. This is the root locus. And to achieve damping ratio 0.174, this is the zeta line. And this is the dominant pole. Okay, the dominant pole is 0.694 plus minus J 3.926. That is obtained from the root locus. Okay, remember this is the one without PI controller. And the gain is 164.6. If you have a graph paper, then you can calculate gain. L1, L2, L3. Okay, L1, L2, L3. This one I took from the book. And if you use if you use MATLAB, you can directly obtain those values. And here is the third pole, S equal to minus 11.61. The third pole. The third pole. Okay, my question is second order approximation value. A second order approximation value. Anyone can help? How to check whether second order is valid or not?
Oh, sir, it needs to be 5 times larger.
So is it valid for this case?
Invalid.
Invalid? Why?
From 2 to 11.61, right? Oh, no, sir, it's valid from minus 2 to minus 10. It's valid.
We check the pole, the dominant pole, and the third pole. Okay, it is actually 11 divided by 0.6. 9 is more than 5. Okay, so it's valid. The second order approximation is valid because it's more than 5 times. The distance is more than 5 times. Now find settling time, TS, and peak time, and error. I want you to get all these things. Settling time, peak time, and error for the system. Please calculate now. How to calculate TS? Anyone can help? What is the value of TS? Four over zeta omega n, 4 over 0.694 is equal to 0.694. I don't have the value. This is the value for TS. TP pi over omega d. Omega d is 3.926. Okay, we have TP, TS, and error. How to calculate error? Error is 1 plus TS 5 over 764. TP 0.8. 0.8 second. Error is 1 over 1 plus Kp. Why Kp? Because it is mentioned that the input is a unit step input, So Kp is limit s to 0, Gs. Okay, then Kp is limit s to 0. Our Gs is here, 1 over minus 1, minus 2, minus 10. S plus 1 to 10. and we have K. So K here is the one at that point, 164.6. K. So Kp, if you calculate, become 8.23. Therefore, the error is 1/1 plus 8.23 equal to 0.108. This is the error. So we have settling time 5.764, peak time 0.8, and error 0.108. Error is not 0. Again, because the system is type 0 and the input is a unit step input. It won't be 0. It will not be 0. Any question here? This is very basic. In the exam, maybe one or two marks to find all those things. Next, let's see what happened if we add a PI controller of this. S plus 0.1 over x. That means we add 1, 0 at minus 0.1 and one pole at the origin. So here, you can see here, 1 pole, 0, 1, 0 at minus 0.1. The root locus is quite similar because the root locus from the pole at the origin is going to the pole, the 0, near to the pole. Okay? So we add pole at the origin and 0 at minus 0.1 with the same damping ratio, 0.17 for damping ratio. The dominant pole now is here. This is the dominant pole, minus 0.678 plus J 3.837. Okay, remember the original one is 964 plus J 3.926. It will be slightly different because we add pole and 0. But you see not much different. Okay? The compensated closed loop pole here, and the gain. K here we obtain as 158.2. Previously it was K164.6. Okay, of course it will be slightly different. It will be different, but it is just a slight different. Approximately the same as the one without controller. Therefore, the transient response is, we can say, is maintained. We can calculate TS 4/0.678. It will be quite similar to the previous one. We can calculate TP also, pi/3.837. Also will be slightly the same, will be quite similar. But the good thing, now system become type 1 because we add pole at the origin. So if I calculate Kp is limit s to 0, Gs, and Gs now is become, previously it was s plus 1, s plus 2, 10. Now we have 0, 0.1, and another pole here. And Kp, when we substitute, get the value become infinity because of this S, and therefore error become 0. This is the application or the on how to use PI controller. This is the benefit of using PI controller. We can maintain the transient response, but we can obtain 0 steady state error. That is the most important thing. Any question here? This is shown here. The graph, the black one is the one without controller, without PI, and this one with PI, controller. You can see that the error is 0. The input is 1, output is 1. It was previously here is 0.108 error, now becomes 0. And the response, the transient response, you can see, of course, there is a slight difference. Not exactly the same. You can see the blue and black lines, they are not exactly the same, but almost similar. Okay? But error now becomes 0. That is the use of PI controller. Let's go into detail of PI controller. The transfer function of PI controller, we normally put transfer function GPI controller. Is normally we use KP. KP is P means proportional. P. KP, that means this P is, we have KP plus KI, integral. This is gain for proportional, this is gain for integral. All integral, because integral we divide by S. This is the transfer function for PI controller. It can be also written as is, I put S at the bottom. So KPS plus KI. And also I can take out KP here. S plus KI over KP over S. This is similar to the one that we just returned. K S plus Z over S, or S plus A over S. I use A better. S plus A over S, where A is KI over KP. In the note I use S equal to minus Z, or S equal to minus A, the same. Okay, here I use Z. PI control is designed by adding a pole at the origin, S, and a 0, and S equal to minus A. A must be small. Choose the 0 here close to the origin. For example, 0.1 or 0.01, negative. The 0 is chosen to satisfy transient response specification. As I mentioned, 0 is used to maintain the transient response. And the value can be adjusted by varying Ki over Kp, by varying the value of A, Ki over Kp. So that is PI controller, S plus A over S. And this is the way to implement PI controller. Okay, we have two separate blocks, but they are summed together at the summing junction here. You can see that the one here is Ki plus K2 over S. It's the same. It's Kp, Ki over S. Here we use Ki and K2, K1 and K2. K1 is Kp, K2 is Ki. Normally if we want to further detail out PI controller, we plot in this, we draw in this block diagram. Otherwise, it's just like this. between GPI. Okay, KP plus KI over S is here. Or if you want to detail out, it will be like this. We can separate into two blocks and they are added at the summing junction. One example, another example. In the exam, just for your information, in the final exam, in the test, we normally do not ask PI controller alone because there is no calculation for PI. It's just S plus A over S, and A is small. So normally we do not ask PI alone, except we may ask about theory, how it works, why we add pole at the origin. So you have to know that. Okay? But PI later will be added in PID controller. PI plus PD. That will be used. That is useful. That will be asked in the exam, PID controller. Okay? For a unity feedback system, given transfer function is here, design a PI controller to achieve the following time response specification. We want overshoot 10%. We want zero steady state error to a unit step input. We want the same settling time as the one before compensation or before we apply controller. We normally solve this, but this is just an example to second order system. It is, we can calculate by hand actually, but normally to show, we will use root locus to get the value. Another difference about this question, you can see that it is written in this form, 2s plus 1, which is not familiar to us. Okay, this is normally used in process control. People in process control, they normally describe transfer function in this term. They normally want plus 1, 2s plus 1, 3s plus 1. Okay, so we need to convert into the form that we are familiar. That means I can take out at 2 s plus 0.5 for the first one here, and I take out 0.5 s plus 2. If I calculate, I get k here 1 just s plus 0.5 s plus 2. Okay, so if you are given in this form, then you need to transform into the one that you are familiar with. So we know the pole is at 0.5 negative and minus n negative 2. The system here is shown, is mentioned as a unity feedback system. So we can draw root locus, draw or sketch a root locus. Here we get minus 0.5 and minus 2. We know this is locus is here. It will go out like this. Okay, because asymptote, there are two asymptotes, 90 degrees and 270 degrees. And we can find this point. The breakaway point, what we call you can find the breakaway point. Is given here actually minus 1.25. If you calculate, you get minus 1.25. And we want overshoot 10%. Then we can get zeta. you can use the graph that will be given to you. Zeta is 0.59. Zeta 0.59. So we can plot here, zeta line, zeta 0.59. Of course, there is an angle here. I'm not sure the angle here. And you can get this value. Okay. If you check, I've actually, you can draw yourself. I've actually have plotted using MATLAB. Sorry, not that clear here. Is mentioned here, zeta 0.5. S here is minus 1.25, J 1.71. Then we can get TS 4/1.25 will be 3.2S, 3.2 second. TP we can get pi/1.71 is 1.83 second. Is here. I already calculated here. And K, if you calculate by using the formula L1, L2, K equal to L1, L2, we get about 3.47. Here I obtained from the MATLAB. And error is 1/1 plus Kp, in which Kp is 3.47 over, if you calculate over 0.2 and over 1, 3.47. So 1/4.47, 0.226, error. Any question here? The first one, the one without PI controller. Next, we move to the one with PI controller. With PI controller, we will have to add a transfer function here. Here we have 1/s plus 0.5, s plus 2. We will need to add here s plus a over s. And later we have k here. This is known as PI controller. As I mentioned, the problem here is what value of A to be used. Okay, sometime in the exam it is given, but in this example it is not given. We have to choose the value of A. Okay. The value of A must be small, can be 0.1, can be 0.01. Here I will take 0.01, small, near to the origin. Okay, therefore we can draw another root locus. We have pole here at the origin. We have another 0, very small here at minus 0.01. We have a pole minus 0.5 and minus 2. There is a root locus here, cancelled out by pole and 0 here, and then another root locus here. Also, we go like this. And if you check, it will be also about here, about minus 1.25. And if we do another zeta line, the same, 0.4, 0.59. Zeta line, we get this point, which is 1.68 J. Okay, when we compare, it was 1.25 plus minus J 1.71. This is 1.25 plus minus J 1.68. It is slightly different. Okay. I also I will show later. I also plotted using MATLAB. And then we can calculate error. You can calculate TP pi over 1.68. You can calculate TS 4 over 1.25. This will be the same, 3.2 seconds. If you calculate this is 1.87 seconds. It was 1.83 without controller. The one here is 1.87. But error will be 0. If you calculate, will be 0. This is the use of PI controller. Error will be 0 because we increase the system time from 0 to 1. And we managed to almost maintain the transient response in terms of peak time and settling time. And if we plot, it will be slightly the same graph in the transient response. Any question? This is the one. This is the real actual one. I plotted from MATLAB. I plotted using MATLAB. See, we add 0.01 here. There are two. There is one pole 10 here, and this is the pole. And zeta 0.59. This is the dominant pole. And of course, we can calculate. We can calculate TSTP and K, and error will be 0. This is just to show to you the one from MATLAB. But it is the same as what we did just now. That is PI controller. In the next lecture, we will move into the next controller, which is proportional derivative controller. Okay? The next controller is a bit more difficult. It needs calculation in order to obtain the value. In contrast to PI, which is we only take a small value. Any question? If not, I will stop here. We will continue on Thursday on PD controller.